Hello there, and once again we are going to answer a question together from AS Physics, and today I have with me a lightsaber. And it's just going to point out what we're doing. We're on January 2008 and it's module 1, force and electricity, and we're going to go for a motion question. So let's get stuck in. We're on question 3. So on question 3 it reads: a hotel lift initially at rest moves vertically in a straight line. From time t equals 0 it accelerates uniformly until t equals t1. When it accelerates suddenly decreases to 0, when its acceleration suddenly decreases to 0, it continues moving until t equals t2 with 0 acceleration. It then decreases uniformly, coming to rest at t equals t3. Whew. The top graph in figure 3.1 shows how its acceleration depends on time t. So let's get to grips with what this means. It means, first of all, it's not moving, and it's moving in a straight line whenever it does move, and it accelerates. This first section here is accelerating, then its acceleration drops to 0, so this means it's going at a constant speed, 0 acceleration, and then it decreases uniformly, coming to rest. So this is then it's slowing down or decreasing. Now, as I scroll down, we see some axes and they are blank, and you may think that we're going to be asked to draw some graphs, and you're thinking correctly. And here we go. It asks, on the middle and lower axes, sketch the graphs to show variation of time of the velocity v of the lift, and then the displacement s of the lift. I already mentioned a wee bit about its velocity in just describing what was happening there. So let's start then with the velocity. Now, in the question there it said it's initially at rest, so we're going to start down here, and we're going to then move in a vertical straight line, and the acceleration is constant to begin with here. So if it's a constant acceleration, then that means as time goes on, alright, here's our time axis along here, as time goes on the velocity is increasing. So that's just going to be a straight line up to here. So there we have it. Next up we have a no acceleration, so whatever speed it was there, it's not accelerating anymore, so it's going to keep on going at that speed. So that's meant to be a flat straight line, by the way. Anyhow, the last section then, it's the acceleration is negative, so it's really slowing down, so we just have to show that. Well, if the velocity is trying to show that it's slowing down, then it's going to drop from this high reading here down to here, so I'm going to drop the level down to here. Brilliant. Now, of course, the next bit is the displacement. Wee bit trickier, but we'll give it a go, and we'll use the velocity time graph to help us with this. If an object is speeding up, then that means every unit time along here it's covering greater and greater distance every unit time. So how we show that on this type of graph is a slope, and that is a slope that has a gradient that increases a bit like this, curving up. Now, next section in the journey we have constant velocity, and what that corresponds to in a displacement time graph. Well, if it's a constant velocity, then every unit time the displacement is the same each unit time, so we're actually going to go for a straight line here with a constant slope. And let's just quickly look in at the last section here. What we have is the object slowing down, so that means this first instance the distance that it's covering is greater than the distance or displacement that it's covering at the end here. In fact, it will get to the point where it stops. So how do we show that? Well, again, it's going to be a curve a bit like the first section, but the curve, the change of gradient of the curve is going to go from a steep gradient to a shallow gradient. And let's have a go at this next section then. So a typical jet, let's just get my lightsaber going. A typical jet aircraft accelerates from rest for 28 seconds, leaving the ground with takeoff speed of 270 kilometers per hour. And we're asked to show that a speed of 270 kilometers per hour corresponds to a speed of 75 meters per second. So we're converting this unit, kilometers per hour, into this unit, meters per second. First bit we're going to do is probably the easiest bit, is K. We're going to change for meters or kilometers into meters. So this K stands for 1,000. So we expand that out, there's our 3 zeros for 1,000. And then last bit, this is per hour, so we need to get per second. So we have to put down this number divided by how many seconds there are in an hour. So 60 seconds, 60 minutes, 3,600. So that's just going to give us the calculator 75 meters per second. There we go. Next up then, we are to assume that the acceleration of the aircraft is constant. Calculate the acceleration of the aircraft as it travels along the runway. Acceleration is our unknown here, and what we're trying to then use to find out the acceleration, well, we've got it's starting from rest, so u is going to be 0. Our time is 28 seconds, and it leaves the takeoff at 75 meters per second. So we use all of that, write that down, and this is going to be using an equation of motion. So we've got AU, V and T, so V equals UT, U plus AT, and put the numbers in. Put the numbers in, that's what we get. So 28A is 75, so what then will 1A be? A works out to be 2.68. Now, last part of the question then asks us to calculate the minimum distance the aircraft travels along the runway before it takes off. So if we're trying to calculate the minimum distance, then yes, we're trying to work out the displacement, that's our unknown, and let's fire down what we know again. So you might notice that I haven't written down that we have A, and the reason for that is because we calculated that. We know for certain that these are true, so if we only use these, then we can be a bit more sure that we've got S correct. Now there's our equation of motion that we're going to use. There's the numbers into the equation, and whenever we multiply it out, we get 1,050. So let's have a look at our mark scheme, see how we got on, and I think we did okay. Deserves a tick. Brilliant.